nice. And now what can we buy with scrap?
We're going to review.
Our lightning rods are on sale. Definitely gonna buy that
let's make a review about the previous lessons. Okay. Okay. So in the lab, the the laboratory that we had in the module 2 of the PyTorch about the MNSC image classifier, right? Okay, it's our first image classifier laboratory. Okay, so the purpose of the laboratory is, okay, the main goal of this laboratory is to build a complete image classification pipeline using PyTorch, from loading the MNST datasets to training and evaluating a neural network model. By the end of the notebook, the model is able to predict handwritten digits from 0 to 9 from grayscale images. The lab brings together data loading, device management from the CPU or GPU, model definition, training loop, and evaluation. So, we're going to import the required libraries. The notebook starts by importing the essentials libraries. Torch, core PyTorch library for tensors and autograd. Torch.nn, used to define neural network layers and loss functions. Torch.optim contains optimizer like SGD and Adam. Torch Visions datasets provides the MNST dataset. Torch Vision that transforms, handles pre-processing and normalization. Data loader used to batch and shuffle the datasets. So, 3. The device, let's talk about the device management, the CPU and GPU. The notebook explicitly handles device placement. It checks whether a GPU CUDA is available. If available, computations run on the GPU. Otherwise, they run on the CPU. The device is stored in a variable and reused throughout the notebook. This is critical because PyTorch does not automatically move tensors or models between devices. Both the model and data must be on the same device to avoid runtime errors. So let's talk about the data preparation and transforms. So the data set we use is MNAST dataset, 60,000 training images, 10,000 test images contained. So each images of the MNAST dataset contains of 28 by 28 grayscale. So the transform is applied. The notebook applies two main transformations. One, to tensor. Convert images from Python image library format to PyTorch tensors. So we convert it. Scales pixels values from 0.25 to 0.11. So when we apply the transforms, to tensor converts images from PyL or Python image library format to PyTorch tensors. So this scales pixels values from 0 to 255 will become from 0 to 1. So we normalize it like mean and standard deviation. We uses the MS specific values. So the mean is 0.1307. The standard deviation is 0.3081. The standardization improves training stability and convergence. Data loader setup. The training and test datasets are wrapped. So the data loader setup. The training and test datasets are wrapped in data loader objects. Okay. Key concept demonstrated here is batching. Data is processed in small groups instead of all at once. Shuffling. Training data is shuffled every epoch to reduce bias. Batch iteration. Each loop yields inputs and targets. This is where the model receives data in manageable chunks. Let's talk about defining the neural network model. The model is implemented using custom Python class that inherits from NN that module. Model structure. Input layer receives flattened 28 by 28 images or 784 features, one or more fully connected linear layers. Rel activation introduced non-linearity. Final output layer has 10 units, one for each digit class. So the forward function defines how the data flows through the network. Input is flattened, passed through the linear layers, activation functions apply. Final logics returned. Raw scores, not probabilities. So here is the loss function. The notebook is uses the cross entropy loss. Why this loss is used? This is designed for multi-class classification. Internally applies log softmax. Expects raw logics from the model. The loss value represents how wrong the model predictions are compared to the true labels. Optimizer. An optimizer is created to update the model weights. Common choice in the notebook is SGD or Adam. Uses a defined layering rate. The optimizer's jobs to read the gradients computed during backpropagation, adjust weights to reduce the loss. So here it comes a training loop. This is the core of the notebook. Each training iteration follows the standard PyTorch pattern. Number 1 is forward pass. What it does is inputs go through the model, predictions are generated. And the loss computation. Predictions are compared with true labels. Zero gradients clears old gradients from the previous batch. Or is backward pass. Backward loss at backward computes gradients. Optimizer that step updates model weights. The loop runs multiple epochs allowing the model to gradually improve. So here comes the evaluation phase. After training, the model is evaluated on the dataset. So the key evaluation practices here is model.eval is used to switch the evaluation mode. Gradient computation is disabled using the text.noGrade. Predictions are compared against true labels. Accuracy is computed. This step measures how well the model generalizes to unseen data. So let's talk about the key PyTorch concepts and reinforce here. So this lab reinforces several critical ideas. The tensor must be on the same device as the model. Gradients accumulate unless manually cleared. Loss functions measure error, not accuracy. Optimizer use gradients to reduce loss. Training and evaluation models behave differently. And so here is the overall learning outcome that we had in this laboratory. By completing this notebook, you'll learn how to build a complete image classifier from scratch, work with real datasets using PyTorch, understand the full training pipeline, avoid common beginner mistakes in device handling and gradients. So this lab serves as a foundation for more advanced deep learning tasks, including convolutional neural networks and real image datasets.